I'm pretending it's 4 o'clock, even though it's 2 o'clock here in Southern Bay. It's cider.
Hi, everyone. Welcome to the Learning Salon. John is pretending it's 4 o'clock somewhere, as we heard. We're very excited to have Zenna today. Unfortunately, Jovo couldn't join us today, but we will hopefully ask the kinds of questions he would ask for him. So before John introduces Zenna, I just want to remind everyone who might be their first time here that the Learning Salon is an interdisciplinary forum. We meet weekly and we discuss contentions and bridges between biological and artificial learning. We really would like interdisciplinary folks to ask questions. So there is ask a question button below. Feel free to ask a question there and vote on each other's questions. If you have a clarification question, please ask it in the chat. And there are no bad questions. If you're a junior person, we really encourage you to participate in the chat. And then at some point, depending on the sort of the flow of the sort of the conversation, we might invite some of the folks who have asked some questions to the screen. So if you don't want to show up on screen, please mention ask for me next to your question. And then, Zenna's mom is here. Hi, Zenna.
Yeah.
The first time we have this, so I'm very, very happy about it.
That's so awesome.
It's really cool.
Hi, Mom.
I'm envious. Right. So if you're a junior person, do feel free to ask a question. If you don't want to appear on screen, that's okay. You can ask in the sort of ask a question or in the chat. Yeah, so with that, since we started a little later because we were submitting our NeurIPS submissions, and so congrats to everyone who made it to submissions. I pass it on to John to introduce Zenna.
Hello, everybody. It's always a pleasure to introduce our guests, but it's a little different today, how special it is. Especially now that I've found out that Zenna's mum is on. I actually want to say that I got to know Zenna and his brothers completely unrelated to work through personal issues, which I won't go into, but just to say that Zenna is one of a trio of extraordinary brothers who I am in awe of and have had the honor of getting to know. And Zenna has become a really good friend, and I deeply miss the wonderful birthday party in Brooklyn that we went to for you, Zenna, and that kind of atmosphere. I hope that comes back. But not only is Zenna a wonderful person and a great friend, but he's also a true intellect, and it was through the Salon, actually, and Zenna sort of becoming a regular guest that I began to realize we had far more in common in terms of our interests and how much I could learn from Zenna. So, Ida and Jova and I have been trying to get him on for quite some time. And so finally we've got you. So Zenna, we don't, I take Ida's lead here. We don't usually go through credentials, but I do think it's quite exciting that Zenna's about to have a change of intellectual venue. He did his PhD and a postdoc at MIT, and now is about to take up a position as a PI and Innovation Fellow at the Zuckerman Institute and at Columbia University. I hope that's okay to tell everyone, Zenna. I think that's really awesome. Congratulations.
Thanks.
And Zenna is going to try and do what one would not expect him to do, which is to have it all. We'll see how that goes. But his intellectual interest has been about reasoning, and he's a total nerdo geek, which is fabulous. And if you want to know more about his work, you can go to his website. But without further ado, Zenna, honestly, it's very wonderful and moving to have you here, and we're looking forward to your talk. Welcome.
Awesome. Thanks so much for the introductions. Okay, I'll try and share my screen. That will be the hardest part of this talk. Okay, so let me just go.
Works perfectly.
Great. Where is that? Okay, everything good? Can you see my screen?
Yes, all good.
Oops. Okay, so hi everyone, my name is Zenna Tavares. I'm a postdoc at MIT. As John said, I'm soon going to be moving to Colombia. And today I'm going to talk about machine reasoning insights from the Copernican revolution. So around across the 1500s and 1600s was a period of quite dramatic upheaval in our understanding of how the physical universe works. This period is sometimes called the Copernican revolution. It has many different actors, but the main cast involves Copernicus, Galileo, Kepler, and Newton. It's a remarkable, perhaps the most remarkable period in the history of science. But as you probably know, I'm not a science historian. The question that I have is, what is it about human minds that enabled these individuals with relatively small amounts of data and kind of relatively simple instruments to conceive of a universe vastly beyond their ability to perceive? And in particular, can we take some of those insights and distill those into principles or algorithms that we can build into our machines? So I'm going to try and do two things in this talk. One is to introduce a paradigm that I work in, which we sometimes call causal probabilistic programming, and present that as a compelling paradigm to account for at least some of the things that these individuals are doing. But two, to also highlight the gap, in the sense that there's still a large difference between what these people and all people are able to do and what the best of our paradigms can do. So this is very early work. I'm taking advantage of the fact that this is a salon and not a normal kind of conference or venue to mostly speculate. So don't expect concrete results, but I hope you'll bear with me. So for around 1,000 years, the dominant theory of the universe was set for systematized by a person called Ptolemy in Roman Egypt. And this was, kind of the accumulation of many different ideas before him. And I'm just going to focus on one particular thing about this model, which is that there's a strict delineation between the region around and including the Earth, which is thought to be corrupt and changing and under the domain of physics, and what is beyond and including the Moon, which was the celestial area, which was thought to be perfect, unchanging, and actually outside of the domain of physics. And one particular thing about this model is that things in the celestial region were bodies in the celestial region were thought to be perfect spheres. Now, the problem was that if you look up at the Moon, which people have done since people have existed, it doesn't look like a perfect sphere, in the sense that it has these kind of irregularities and unevenness on the surface. And so people tried to explain this in many different ways, while still remaining in this general framework. So they thought perhaps it's a reflection of the Earth's oceans, or perhaps it's defects in our eyes, or perhaps it's variations in the density of the Moon. And there's actually a fascinating ancient text by a philosopher called Plutarch, where he goes through many of these different arguments. And then in 1609, everything changed. So Galileo, kind of furnished with a new telescope that he had got and improved, looks at the Moon in a clarity that nobody had done before. And he concludes the following. He says, "I feel sure that the surface of the Moon is not perfectly smooth, free from inequalities, and exactly spherical, as a large school of philosophers considers, but that on the contrary, it is full of inequalities, uneven, full of hollows and protuberances, just like the surface of the Earth." So the question I have is, how did Galileo do it? What is it in his mind that allowed him to conceive of this new theory, which was against the prevailing wisdom? And so here's a kind of an answer that I'm proposing. One, that Galileo maintains a prior belief of a possible theories of the Moon. Two, within each theory, Galileo can conceive of plausible ways the Moon would appear. And third, as he looks through his telescope, he uses inference, probabilistic inference, to revise his prior beliefs into posterior, i.e. post-evidence beliefs, in the sense that theories that are unsupported by the evidence become less likely, and those supported by the evidence become more likely. So what do we get from this formulation? Well, the answer is that we're increasingly being able to build machines that can do this kind of reasoning in silico. And so let me just sketch out how we try to do this. And again, we're just in the early days, but we will consider two different theories. So one theory is this kind of rugged moon, Earth-like moon, which is mountainous, put forth by Galileo and Plutarch. And the other theory we'll consider, which we'll call in T-sphere, is the idea that the Moon is a perfect sphere, And the discoloration, sorry, the unevenness in the coloration of the moon is due to corruption from the Earth. This is one of the theories put forth by Aristotle. And so the first thing we have to do is construct a prior distribution over different theories. And so we can encode the fact that the Aristotle Telemetric theory was dominant by giving it a high prior probability. And then within each model, we have these kind of model-specific parameters, which we have to be uncertain over too. So for example, in the T-sphere model, we have to encode for every point on the surface, what is the surface discoloration? And for the rugged Earth model, for every point on the surface, we have to encode, how high is the mountain? And then for both of these different models, or for either of these models, we have to take that geometry and render it using an algorithm similar to the kind that we find in video games and animations, ultimately to produce a final image. And I'm calling this a hallucination because it's, in some sense, it's kind of like a possible imagination of how the world could be, or how the mood could be. And so in reality, we don't express these models in this schematic, we use programs. And so what I'm showing you here is a program, or at least a kind of program in a probabilistic language. And I'll just kind of break down 3 different parts. So the first part is that we express our uncertainty over these theories using these random variables. So again, as I said earlier, we're not sure whether it's we're not sure whether the model is T-sphere or T-rugged. The next part is simulation code. So this is similar to a program in any programming language that you've already used. And again, I'll just model in what I showed you in the previous slide. And then the final part are conditions. So these are our data. And so what I'm showing you here are kind of prior samples from our model. And again, this is essentially randomly choosing a value for all of the random parameters, and we get different random results. And so we're varying both the lighting, where the moon is relative to the sun, the relief, which theory we're in, and so on. Now, so again, this is early work, so we haven't completed the inference yet. And so what I want to show you is the experiment that we're running and what I expect to see. So in some sense, this is a kind of pre-registration. So the question that I have is, what is it about Galileo that made the difference? The common knowledge in history is that he had a telescope, right? And so what we should expect to see is that if we look at the posterior distribution over these different theories, right? Again, these 2 theories are the rugged theory and the spherical theory. As a function of the magnification, where one is when we see with the naked eye, and Galileo's telescope was around 20 times, we should see a transition from the naked eye, magnification 1, the posterior being dominated by the spherical model, to it switching as we get closer to Galileo level magnification, to it being dominated by the rugged model. And so let me just explain why that should be true. So at a high level, the answer is just that seeing is believing. If I look at the moon, with a good magnification, like on the left-hand side, I can simply see, the mountains, right? But what does that mean from a Bayesian perspective or a probabilistic perspective? Well, one way to think about it is that, it's conceivable that this moon on the left-hand side is just very carefully colored in just to, coincidentally get all the shadows in the right place. But it would be a very suspicious coincidence. And in some sense, the Bayesian paradigm says that very, suspicious coincidences are very unlikely to be true. Or in other words, the possible worlds in which, that theory, the spherical theory, is consistent with that data is quite small. Okay, so this is how we're trying to use this probabilistic generative account to kind of model how Galileo came up with theories of the moon. But let's look at what Galileo actually said. So he says, the boundary which divides the part in the shadow from the shining part does not extend continuously in an ellipse, as would happen in the case of a perfectly spherical body, but it is marked out by an irregular, uneven, and very wavy line. So in some sense, Galileo is given an argument about why the moon must be rugged. And he's come to the same conclusion that we're trying to get to using this probabilistic inference, but he's used a different kind of way to get there. So the question is, like, what is this? What is this kind of argument from a computational perspective? So one thing we can do is try to break it down a little bit into these 3 steps. So in the first step, we're going to assume that the world is in fact a perfect sphere. And a consequence of that is that the terminator, which is the line between the dark and the light side of the moon, is going to be a perfect ellipse. But in step 2, we know that it's not a perfect ellipse because we can look at the moon. And so in step 3, we can conclude, therefore, that this theory is false. So another way to express the same thing is in this kind of derivation tree. And so I'm not going to go into the details of what this tree means, but I will say a few things. So one, these are the kinds of trees or derivations that we use in mathematics. And so at the bottom of this tree is the proposition, the thing that we're trying to prove. So in this case, it's that the moon is not a sphere. And then we have a kind of a chain or a tree of different steps of reasoning until we get things at the top are axioms, right? And the second main point is that mathematics is the enterprise of proving things, but proofs themselves are mathematical objects, and so we can encode them in machines and verify them. And so here's my proposal, my very rough proposal, is that we need to extend our languages for probabilistic reasoning and inference with the ability to construct proofs and arguments. And so just as we have a generative component, we need a kind of a proof or an argument component. But there are a few, I think, key differences we'll have to have between these kind of proofs and mathematical proofs. One, a proof is made up of these propositions, statements, things that are true or false. We want to make sure that these statements are, in some sense, grounded out by our model. So if we say that, for example, it being a sphere implies that the terminator line is going to be a perfect ellipse, then that claim should be something that we can verify relative to our models of how light works in our generative component. And the second thing is that mathematical proofs are in some sense too high of a burden, right? For the most part, we never really know things are absolutely true, absolutely false. So we need to make sure that we encode a kind of soft, argument where we can say the things that are likely to be true into our proof structures. Okay, so again, there's my high-level sketch of how we can encode, not even how, like what we should do to be able to augment systems that can reason, to be able to reason in the way that Galileo reasoned to conclude that the moon was in fact mountainous. So going back to the Telemetric model, the second thing I want to focus on or look at for the moment is the fact that the Earth is at the center. So Copernicus, here's Copernicus, his main thing was revising that and concluding that the sun is actually at the center of the universe. And so the thing I want to think about with Copernicus is, okay, so if we think about, like what kind of thing is Copernicus's theory? So in this page, I'm showing you a few different theories: Copernicus's theory, Telemetric theory, Newton's theory. And all of these different theories are some kind of point in some kind of space. And so the question, I think a basic question that we should try to answer is, what is this space of theories? So let's go back a little bit and look at this Telemetric theory that we've been running with so far in some more detail. Many of these things I've said already, but a few more things such as, we have kind of a nested Russian doll-like spheres inside spheres inside spheres. Every sphere is moved by some kind of mover or spirit. There's many different details about this theory. So what is this theory? How can we represent it? So my claim, which may not be surprising at this point, is that these theories are programs, or at least they're well captured by the programming formalisms that we have. And a lot of that programming formalism will be shared with the programs that you're familiar with, but we need richer languages. So we need to be able to express laws about the world, things that we are sure are true. We need to be able to express time. We need to be able to express uncertainty. And so my sketch of how Copernicus reasons is that, one, he represents theories, at least mentally, as programs. And two, similar to Galileo, he has a prior belief over possible theories. And he uses inference to revise his belief over theories given the evidence, using exactly the same laws that we've seen so far. The difference here is what is the space over which he has hypotheses. In this case, is programs. Okay, so doing inference or searching over programs is a very hard thing. A lot of the people in my lab, in the lab I'm in, and the labs I work with, really try and focus on this program. How can we search over program spaces? How can we do inference in these complicated spaces? And it's a very hard thing to do. But let me just give you a sketch of a naive approach. So one naive approach is to say we start with some candidate program or model M, we randomly modify M, and then we look at the likelihood of the data under the original M and the modified M. And if the new M is a lot better in the sense that the likelihood is a lot higher, then this becomes our new current state. And if you repeat this process again and again, you're going to get a sequence of models. And if you do this carefully, you can make sure that that sequence of models actually samples from the posterior distribution. In practice, it's just extremely hard to do this, and it won't work in any finite amount of time. And so we need better methods. But more fundamentally, is this how Copernicus really came to a heliocentric model of the universe? So one thing I've been thinking about a lot is some work, this is a paper that you should read. And the idea is that perhaps the way that we build theories is a little bit different to this kind of stochastic search. So Laura Schultz, who says in this paper, finding new facts, thinking new thoughts. The first kind of knowledge that could help guide a learner's search for new ideas is an abstract representation of flaws in her current theory. So the point here is that we don't just do a kind of random search over theories. We have a theory, that theory is wrong in some particular way, and we use the way in which it's wrong to revise our current belief about our current model. So can we take that idea and turn it into an algorithm? So here's a sketch of an algorithm. It's not much more than a sketch, but the idea is that we have some current candidate model M. This makes some predictions, and we try and find the error, like the way in which these predictions deviate from a model. And then we try to explain this error. So we construct an explanation like, why do we have this error? Is it something about our model? Are we using the wrong model? And then ultimately we have to revise our model according to this explanation. Okay, so one of the things, so we're still trying to make this very abstract idea a more concrete idea. And one domain in which we're doing this prior to doing it in kind of the celestial mechanics is in this new domain we've been working on. We call the kind of the framework Autumn. And we are really trying to build this small kind of grid world-like domain of causal models to experiment with different ways of reasoning. And so this is some work that I initiated, but it's really been taken over by an undergrad I've been working with called Ria Das. And so I recommend you check out this workshop paper we have, and we can talk more about this in the discussions. Okay, so the last person I'm going to talk about very briefly is Kepler, probably my favorite of the bunch. And Kepler's known for Kepler's laws, finding that the universe is the planets move in ellipses rather than circles. But the more interesting part for me is Kepler's imagination. So he says something like this. He says, if the Earth and the Moon were not kept in their respective orbits by a spiritual or some other equivalent force, the Earth would descend towards the Moon 1/54th part of the distance, and the Moon would descend the remaining 53 parts of the interval, and thus they would unite. So again, the question is, how does Kepler do this? How does he conceive of this world which actually isn't real? So again, I've got my 3 steps, but this is a little bit different to the previous cases. There's some shared structure, which I'll say now, which are these first 2 parts. So one is Kepler again maintains a prior belief over possible theories of the universe. Second, he uses probabilistic inference. Using probabilistic inference, he revises his belief over these different theories. But the third step is different. In this updated belief state, he's able to mentally manipulate his model of the world to imagine how these hypothetical situations would play out. And this is not a probabilistic inference. This is a kind of a causal and counterfactual style reasoning. And so we have a paper which is coming out in the current ICML, or the upcoming ICML, which is really about how you do counterfactual reasoning in complicated simulation models. And I'm just going to give a very high-level sketch. The main thing is that we add into our language this new operator. And so in this case, I'm saying that we have some force. Again, it's obviously just a sketch of a program. We have some orbit. And then we can construct this orbit hypothetical, which is what the orbit would have been had the force been 0. And the system will take this command and automatically construct this counterfactual for you. Okay, so that is my very fast kind of overview of celestial mechanics in the Copernican revolution. And so let me just end with 3 claims. My first claim, and I want this to be somewhat strong so people disagree with me. My first claim is that automatic probabilistic and causal inference in programs is currently the most compelling paradigm for building machines that reason. The second claim is that theorem proving, as I spoke about earlier with Galileo, is a new class of programming languages, which I think really offers the future to really getting machines that reason. But finally, even with that, we're still very, very far from anything approaching human reasoning. There's so many things that we can do and we naturally do, which we aren't capturing with our formalisms. And so with that, I will thank my collaborators, especially Josh, Armando, both of my advisors, Emily, who's been working with me on this project, and finally to say perhaps you. So I'm moving to Colombia and I'm looking for people to work with. And so if this kind of stuff interests you, please, get in touch.
Thank you so much. This was so awesome. If you're a student looking to join a cool lab, do definitely consider Zenna's lab. And we are now going to enter the discussion. I'm just going to try to get John back in. I think that his connection dropped for a second. It was quite wonderful. I really appreciated it.
Thank you.
I think that your little disclaimer up there, do you want to install the updates now, went very well with many of the portraits of Copernicus and Kepler and everyone else.
Should I stop sharing my screen? I can't actually see.
Sure, that sounds good. That sounds like a good idea. While we wait for John to join again. So let me see if I can join him again. He's still continuing. So, oh, there he is. Oh, he's back. Perfect. All right. So, John, would you like to go first?
Yes. I don't know if like is the word, because I'm going to ask lots of... I think it would be helpful, Zenna, I think for lots of people here who aren't as familiar with this framework, to just map a little bit more intuitively the notion of, induction, deduction, abductive inference, and what we think reasoning is before we get to computers, and then why you think you can algorithmize what people thought these forms of inference were long before we were talking about computers and programs. And I mean, I don't think it is intuitive that these notions that have been around for a long time, and Peirce obviously was the person who came up with this notion of abductive inference, why it should yield to this formalism, because one can worry that this is more a metaphor than exact mapping of what humans are doing to what you've drawn out. In other words, is this a metaphor for a computerized algorithmic version of inference, or do you actually think that this is what Galileo, Kepler were doing? So I can't quite decide whether this is to be taken literally or as a kind of useful metaphor that will get us to the first step with what you're doing. I don't think it's obvious that this is a literal mapping.
Right.
Because abductive inference, as you know, there are an infinite number of possible explanations for things. I mean, that was the point that Peirce made, is that you come up with 10 possible theories, you can come up with an 11th. Come up with 1 million, you can come up with 1,000,001. So, and yet we do it, right? Without ever going through a search of all these possible theories and their associated probability. We shortcut that entirely, right? So I'm a little bit puzzled how this works. In other words, we're constantly making, that, as I said to you, that person's got nice clothes, they must be rich, right? They have nice clothes, they stole them off a rich person. They're not nice clothes, they're actually cheap clothes that they've managed to make look expensive. You could go on and on and on and on and on, right? So how can we instantly pick the right one?
We don't always instantly pick that.
Well, but I just want to know, is this a computer science metaphor, or do you think this is what people are actually doing when they see somebody with nice clothes and assume that they're rich?
Right. So there's a bunch of different questions there. So let me start with the last thing you said. Do I think this is what people are actually doing? So the answer to that is yes, approximately. And in the sense that I think the way people reason in a variety of situations is well captured by the Bayesian paradigm. In a sense, they are following the rules of inference. Now, the approximately is a big part, right? Because we always have bounds on the kinds of information that we can acquire, that we have. We have bounds in our computation. So, and there's all the, the kind of the complexity of real life.
But why isn't it a heuristic that it looks like it's Bayesian?
Well, I mean, if it always really looks like it's Bayesian, then like how different is that from
so just so for everyone here and for me, if somebody sees somebody with nice clothes and say she must be rich, just tell me what steps they're going through. Tell me why that can be proven to be Bayesian. How is that done?
So let me answer that in two different ways. So the way in which it's actually done is in cognitive science. I'm not a cognitive scientist, right? But there's many people, some of which are in this forum at the moment, who do experiments to show that the Bayesian model, at least in some situations, not all situations, is the best model that accounts for the actual data, right? And so the way that you do that is that you do experiments as a scientist, right? To empirically verify whether people are actually being Bayesian, right?
So can you just go through the steps? I mean, how would one do that? In other words, I'm just genuinely curious. How would one show that when you take 50 people and let's say 45 of them all just go, that person must be wealthy because she's got nice clothes. How would one go about showing that fairly consistent inference on the part of those 45 out of 50 people is Bayesian? How would you actually do it? I'm just interested in what the experiment would be that would actually prove that they've actually used a Bayesian algorithm implicitly, because presumably they have no clue what Bayes is. So rather than explicitly using their knowledge from watching soap operas and Dynasty and having an idea that rich, how does one go from the explicit notion of nice clothes and rich being wealthy and your experience of seeing celebrities with nice clothes, how does that turn itself into an implicit Bayesian algorithm?
Right. So there's two questions there. So one is how does it turn into an algorithm? The second is how do you test it or verify it as a
So those are my two fundamental questions. Is how does something that seems to be very explicit, based on notions of wealth and celebrity and nice clothes and fashion runways and all that, turn into an unconscious implicit algorithm? That's one question. And then two, how will one prove that?
Okay, so let me start with the second question first. So again, I'm not a cognitive scientist, but roughly speaking, it goes something like this. So first you set up a much more constrained scenario than the example that you have. One where you can either control or manipulate or know the kinds of prior knowledge that you think people have. And two, you construct an experiment. And so you have, to make a very concrete example, there's some work by Peter Vitalia, who's now at DeepMind, and he uses a model to show how people predict what will happen when you have a kind of a block of towers, like where will it fall, right? And so in his model, he has a kind of a simulation in the mind model, very similar to the stuff that I've been saying. And the way you verify that is you look at the actual data, what people actually say, and you say, how well do these different models account for, the actual data that I've got, right? So you treat it as a scientist in any other realm. I mean, again, I'm not a cognitive scientist, so I don't do these kind of experiments. But the basic setup is to construct different plausible models of the human mind. Perhaps they're using heuristics, perhaps they're doing some other framework, and see which of these different models accounts best for the data.
No, I guess what I'm trying to get at is that I'm very familiar with work looking at Bayesian integration, for example, during movement, where you basically integrate inversely with respect to the variance of the different sensory modalities, and it does really look like humans, when they're integrating proprioception and vision, that they really are very close to Bayesian when they do that, right? And of course, they have no notion that they're doing that, right? They're implicitly Bayesian, even though they have no notion. I'm quite happy with that, but what I'm having a genuine struggle with is how one goes from that very implicit sensory integration notion of within his Bayesian to when you're using very explicit knowledge, like what's fashionable clothing, what is not, what does it mean to be rich. What I'm having trouble with is how does one get that explicit factual knowledge into an implicit algorithm that looks basically just like integrating sensory modalities. It seems like they're being considered equivalent in some way.
You mean in principle, or how do you do it, or how do people do it?
I'm just saying, do you see that not as qualitatively different things, where you have to use facts based on semantics and knowledge that are very overt and explicit to do then some sort of Bayesian inference on it, versus the kind of Bayesian inference which is entirely implicit when you do sensory modality integration? It just makes it look like we're doing something very automatic, even though we're injecting into it lots of explicit knowledge that we can articulate. So if I say, why did I think they were rich? They're rich because they have nice clothes. I'll go, well, because I happen to know the prices of clothes and I happen to know what's good. And are you telling me that that verbal articulation that I'm going through is actually a little Bayesian generator underneath that doing that? Is that what you're saying?
Yeah, for the most part. I mean, let me give you an example. So this morning I was making my slides, early this morning, and I got some ice cream because it's a pandemic and I'm still allowed to have ice cream in the morning. And I left a spoon in the ice cream tub and I went to my room to continue working on my slides. And I heard a few minutes later a clang on the floor. And I immediately thought, well, it must have been the case that the spoon fell out of the ice cream tub and hit the floor. So my kind of challenge to you is to give me a paradigm other than Bayesian simulation in the mind, which could account for that relatively mundane act of reasoning, right? It's not just that, it's not a simple sound recognition. It's not I heard some, metal-like sound and I had a classification. I had a model of how I think the world works, and I conceived of plausible things which could have happened. And that was, instantaneous. I didn't deliberately, I didn't, sit down and consciously go through different possibilities. It just came to my mind that must have been a plausible conclusion, but it was based on, pretty high level information about what I had just done, right? And so I guess my answer to your question is, the way that I think about it is that as a human, we have lots of different kinds of knowledge, right? Some of it is kind of low level perceptual knowledge. Some of it is high level kind of declarative knowledge. And we need representations of knowledge which accommodate all of that. And we need algorithms or at least principles by which we can reason coherently. And the
So basically, if I understand you, you think that every form of thinking is algorithmic. There's an algorithm for it.
Well, I'm not sure what that would mean.
Well, you're kind of saying that we should be able to turn into a computation or in algorithmic form any kind of reasoning. I mean, that is what you're basically saying.
Yeah, I would agree. I mean, I think thinking is necessarily algorithmic. I don't think knowledge is necessarily algorithmic. I think those two things are different.
So just so I understand, once you have your model of the world, and we don't know what that is, right? It gets back to the conversations that Ida and all of us have been having about the kind of representation that you work on. And are you saying that if you bracket out the mystery of the different models that you work on, and we don't know how you have a model of the overt declarative kind, but once you grant that we have models, whether it's a set of proprioception and vision implicitly or a model of how communist governments work, after that, you do some sort of implicit Bayesian work on that overt model. So in other words, it's downstream from the model, the process that you would. The operation on these representations, whether they're overt or implicit, can be couched in a Bayesian way downstream of the complexity of the representations. Is that right?
What do you mean by downstream?
Meaning that you operate, you know, there are potential models. You heard the clang of the spoon and the ice cream. You have a model of melting and close to the counter edge, and this, you have quite an elaborate causal model of the world. It's quite overt, and then that thing that you have is what you use to then infer what probably happened, right?
Exactly, yeah.
So I'm saying that the inference is somehow of this Bayesian kind, but it presupposes this varying types of model that you can do this inference on.
Yeah, so you do, so the way in which we represent knowledge is completely orthogonal to inference. Orthogonal in the sense that you can do reasoning with different kinds of representations of knowledge.
Right.
And probabilistic inference and modeling doesn't say anything about how you should represent knowledge. Really, you know, I think sometimes Bayesian inference is extended beyond its reach. For me, Bayesian inference is really just about reasoning with uncertain knowledge, right? So if I have some things that I'm not sure about, how can I make any kind of conclusion? And so, you know, if you ask, you know, are we necessarily Bayesian? Well, I think the alternative of not being Bayesian is always going to be suboptimal, right? And so you may be suboptimal because it's more efficient to do that relative to all of the other constraints that you have. But Bayesianism at its core is just about reasoning with uncertain information, incomplete information. It's the logic of that kind of reasoning. And so it's a very kind of weak claim in some sense, at least in my opinion.
Yeah, I'll just finish by saying that, and this is why this is so educational and for me, is that it just seems to be skirting the real issue, which is the quality of human reasoning is a function of the sophistication of the models that you have available. Right. And this framework has nothing to say about that.
Well, so the framework that I work in has a lot to say about that. So it's not just Bayesian inference, it's Bayesian inference in programs. So the representation here is saying we want to use the power of computation, programming languages to express knowledge. That is where the representation comes in. And I don't think that can express all of the kinds of knowledge that we have, but I think it's the best candidate for expressing a lot of the kind of knowledge that we have. It can express the kind of simulation that I used in the ice cream. It can express the kind of, you know, graphics models that we use to, you know, basically see 3D structure from 2D images. So I am making strong claims about representation. They're just somewhat orthogonal to the claims I'm making about Bayesian inference.
Right, right. And I suppose it's just that I feel that the package of what, you know, we're doing in this discussion, it feels slightly baffling and artificial to me to sort of put a divide between the nature of the representations that we have to presuppose, which are themselves a complete mystery, and then the sort of operational process that one can do across these potential models and with them. I'm willing to believe that you can say that, but it just seems to me that the downstream inference process being similar across implicit and overt situations almost imposes the fact that there's no real mystery anymore, because we can apply this framework to a whole spectrum of representations. It seems to me that it sounds more, it sounds stronger, but as you say, it actually sounds weaker.
Well, so just to clarify on that point, oh, he's gone.
No, I can hear you though.
Okay, so, you know, like within the paradigm of Bayesian inference, you still have to do it. You still have to, you know, compute the thing you want. And within that kind of degree of variation, there's a whole wealth of variety, whether your knowledge is kind of high level declarative or it's kind of low level perceptual knowledge, whether you're working in a continuous space or a discrete space. So it's not all the same. It's just that there are some high level principles which you should adhere to, at least approximately. Otherwise, you know, in some sense, you'll make mistakes. I think we lost him. Maybe not.
John, are you there? Hello, John. So we seem to have lost John. So I'll ask you a question while we find our way back to John, or he finds his way back to us. His computer turned off. Okay, we will. Okay, I'm just gonna let him know. Okay. All right. So, so thank you for that. That was a very wonderful talk. So I'm very sympathetic to the idea that just Bayesian inference is not enough. And it seems like what you're saying is that we need some kind of abstraction into object and entities and do our theorizing on them, as opposed to stay within sort of just probabilities over everything. And so it seems like there is a kind of dimensionality reduction from having infinite kinds of models in mind and just computing probability equally on all of them in a manner of speaking. So I'm very sympathetic to that. There's some things you said that I'm just going to ask a little bit. So why Bayesian approaches? Why not other approaches? Because there is no, there's no reason that is the thing that explains. If there are many different paradigms, and this becomes a little bit of a maybe not quite paradigm level, but maybe computational paradigm level discussion, because these modeling approaches are not too far from one another. Mm-hmm. But why a Bayesian approach as the basis for this sort of more abstract reasoning?
Right. So I guess you could split that into two different questions. So one is like, why Bayesian inference as an account of kind of human reasoning versus like, why should we build Bayesian machines? Like, why should we build AI?
No, if you want to build, engineers can do whatever they want. There is no restrictions on that. My question is the cognitive science question. Why is this proposed as a model of human cognition as opposed to other models? You mentioned to John's question earlier, you said, oh, there are people who run experiments and these explain data, but other kinds of models explain data too that are not Bayesian. And so and then predictions are different. Bayesian models are not neurally plausible. So why should we think about how Copernicus might have reasoned about the stars using a Bayesian approach?
Right. So I'm not sure I would agree that Bayesian models are not neurally plausible or any less plausible than anything else that I've seen.
Wait, I think that's kind of widely accepted though. So could you clarify? Is there what do you have? What is the basis of that?
Well, I guess maybe two bases. So one is, I'll caveat all of this in saying that my domain of expertise is not in kind of neural plausibility. That said, I think one, it's very hard to say something is definitely not neurally plausible. And two, like when you get down to the low level, you can implement a lot of Bayesian algorithms using neural networks or whatever kind of framework of neural models that are that we have at the moment. So there's a lot of, for example, Bayesian inference is based on kind of variational inference based on like gradient-based descent. So I guess I don't see any reason a priori why Bayesian inference is less neurally plausible than.
To be clear, so you think that we need to have explain cognition with a more abstract version of Bayesian inference that it's itself requiring gradient descent and neural networks in order to be implemented. So it's like 3 levels of abstraction and different kinds of modeling as well.
What I'm saying in terms of neural plausibility is that if you want to implement, there are many different inference algorithms which can be, implemented in neural machinery, at least, silicon neural machinery. I haven't seen any kind of compelling claims that the Bayesian paradigm is less neurally plausible than.
Okay, so we can move on from this then.
Yeah.
So just to go back to the main question, that's just like, even if we assumed that you haven't seen any of the many arguments about the lack of neural plausibility of Bayesian models. Let's assume that you've never seen any of them and build from there. Even in spite of that, even if you didn't believe it, even if you had seen them and didn't believe them, then whichever it is, that whatever assumption we take, just like putting that aside, Still, why would you think that the Bayesian approach would be the right way to capture higher level reasoning? Why not other approaches, modeling approaches? And if your answer is, I haven't seen anything else, then please no, not that answer.
No. So you can take a first principles approach, right, which is probabilistic inference. So, the Bayesian paradigm is really just probabilistic inference. You have some uncertain information, and you have some additional information. Now, what should you now believe, right? And so, if you deviate from that, in some sense, you'll always be suboptimal, right? This is kind of the Dutch book argument of kind of probabilistic inference. Like Bayesianism is itself just probabilistic inference. And so you might say, why don't you use a paradigm which is not purely probabilistic? Well, I think, again, if you deviate from that paradigm, you can prove that, at least under some assumptions, you'll make errors, right? And so the foundation of probabilistic inference is like sound reasoning with incomplete information. So this is why I think, kind of a basic level, why it's a solid ground to stand upon. Now, that's not to say that, in practice, everything that people do is just, you can there's a few things. That's not to say that people are explicitly going and computing probabilities of different events, one by one. That's not what we're clicking. Sorry, you're muted. You're mute, so I can't hear you.
Sorry, I'm trying to get John back in.
Oh, sorry.
Sorry, explaining. Wow. Okay. Explaining what Bayesian inference means, again, to me, does not capture the question, or answer the question, which is, why would we think that this is how human brains actually do it, or this is how humans actually do it? So that these are two different questions. You said this is the definition of this, and if it's not such, then it is suboptimal. That is the definition, yes. That is one model for defining things, right? But why would we think that this is the mechanism with which, or the way in which human brains actually do it? It's like, this is one model of doing it. This is one algorithm of doing it. There are many other possible algorithms. Some of them exist. Some of them we haven't even thought about yet. Why would this be the right one? And I know the definition. So it's not that, the question is not what is the definition. The question is why this one is the one to think that this is the way that reasoning happens, especially given what you're arguing is, we need to add a lot to it in order for it to work, actually. We need to sort of make it more abstract, and we need to have it move a little bit more close to, for instance, logic, right? And I'm going to mute myself because I'm trying to get John on, but if my lips move, it's because I'm asking him to join. Sorry.
Yeah. Okay, so, so my point wasn't just to restate the definitions. My point was, I think, again, there's different questions. If you're asking what do humans, actually do, this is an empirical question answered by the domain of quantitative science. And I don't do these experiments, but again, there's a lot of work in different domains showing that people are approximately Bayesian. And I'm sure there's many domains in which they're not. My personal goal is to extract the principles to build and design machines that can reason coherently in the world. And I think once you start from that question, then the Bayesian, standpoint is a natural place to start, right?
So to be clear, so you're saying that you have an engineering perspective. You want to build some machines that can reason, and for that, you can use whatever works for you.
No, so the first part is true, but it's not that I think you can use whatever you want. I think, again,
it works for your goals. So I guess, again, to bring it back to the question I was asking why use this as a model, as the model for cognition. So I'm going to say what I said like 10 minutes ago, which is that engineering argument, I'm totally on board. Engineers can use whatever tool can help them achieve the particular goal that the algorithm has. So they can use whatever algorithmic approach they want if there is a goal. That's a different story. And if that's your goal, you can say that's where I stop. I'm not making claims about human cognition or about biological cognition, and I'm totally happy with that. my question was on the other side. Why use this approach that we know the definition of, that we know engineering can use successfully for many applications, in some less, in some more applicable, but why use this, or why claim that this is the approach for human cognition? And you can say, actually, that's not my stronger claim. I would like to focus on on machines that can reason, and I'm totally happy with that. But my question was on this other side.
Right. So I think there's like a middle ground, or maybe a different perspective. I'm interested in reasoning in the sense that it's somewhat independent of the organism. So I think there's a kind of a pure and kind of implementation agnostic notion of what it means to reason, what it means to acquire information, what it means to come to conclusions. And I think it's probably true that humans do that approximately, right? Again, this is the domain of cognitive science. People can experiment with that. So my point is that it's not just, okay, I'm engineering something and I can choose whatever I want. My point is that if you want to build any kind of system which works coherently in the world with incomplete information, then I think this is the paradigm from which you should start.
Oh, so you're saying it should. It's a prescription that this is the paradigm? Because I would definitely disagree with that. I think a lot of people would disagree with that. I think you might disagree with that.
Well, I mean, okay, so should is a strong claim, because you have to take into account, things like computational resources, but I think of it as a kind of ideal in some sense. Like, this is the ideal, and in reality, we may have to make shortcuts, we may have to use heuristics, but this is the ideal. That's how I think about it. So
I appreciate what you said, and I think that we have arrived at exactly like the core of it. And with that, I just want to read what Josh Tenbaum said, and I want to invite him too. He said, we should use this approach because you can usefully add complementary ideas to it. The idea of probabilistic programs, the idea of reasoning about programs as proofs that move us closer to an understanding of reasoning here than we have before. Well, I would argue that you can do it with other kinds of algorithms too. All of them are, you can add things to them, etc. But and just as I mentioned in the chat, and I said it earlier here, I think your important contribution, and I now want to focus, after sort of clarifying, I want to focus on that important contribution. I think you moved probabilistic sort of modeling to a little bit more abstract level. So if there was a continuum between logic and sort of probabilistic reasoning, I feel like if my understanding is correct, you moved a little bit towards that direction, which might be a higher level of reasoning, which might require some abstractions, and having objects for your theories in a different way. It might require certain levels of generalizations. And I really actually appreciate that. And that, I think, is something that I'd like to hear a little bit more about. I feel like that level could be the same way that you're saying Bayesian could be implemented in different ways. If somebody says gradient descent is not neurally plausible, there could be another way to implement it. Likewise, that higher level, and I think this gets to what John was saying perhaps too, could also have something that's non-Bayesian underneath it. We could build that higher level from different angles. So there is like a multiple realizability of that higher level. And currently you've used the Bayesian perspective. And I think it's a contribution both to cognitive science, and it is a contribution to probabilistic approaches. But that's the point that I think I was trying to make, that at the lower level, it's not necessary to have the Bayesian approach. At the higher level, we don't need the Bayesian approach to reach there. There could be other paths. But at the same time, I think this is a fantastic paradigm, and it's coherent in itself. And I'd like to hear more about that. So I'm going to allow John to finish his comments from earlier while I invite the next guest.
Yeah, I guess, what I'd like when we have the guests come on, what Ida's saying is I'm still trying to understand what you think reasoning means. Okay, so in other words, is reasoning the proper weighting based on uncertainty of a potential set of theories, right? Or is there reasoning within each particular theory, right? Because then it seems to me that reasoning goes into infinite regress, because you can reason about each theory, you can reason across theories. When is it, what is reasoning? Is reasoning the inference step, or is reasoning the construction of the model itself? Which is reasoning?
So I'll give you my answer. So like at the highest level, I think of reasoning as kind of the process by which you come to conclusions, you come to beliefs about the world. And one of the nice things, at least in my opinion, about more expressive representations is that this distinction between reasoning about facts or reasoning about programs or reasoning about models somewhat dissipates. Now, in practice, there may be different algorithms you use, but a lot of the conceptual structure is kind of shared. And so to your latter point, I don't think this leads to an infinite regress. There is a bottom, right? Like, but I do think that you can equally well reason about whether within some model some parameters should be different, or like some things should change, versus saying I need to fundamentally change my model. Both of these, I think, can be captured largely within the same paradigm, although there will be differences in the actual kind of.
So just to understand, if I'm in Athens and there's a flood,
mm-hmm.
and I say Poseidon must be angry.
Mm-hmm.
Okay, so I infer that Poseidon must be angry. But I also, before I ever inferred that, had this belief that there are gods that live in the air and live under the ocean, and
mm-hmm.
that gods control the weather and gods get angry. So I'm just trying to understand, is the kind of reasoning that leads to the construction of the god Poseidon in the first place the same as the kind of reasoning that you make that given that we've just had a flood, Poseidon must be angry? And I'm just trying to understand, are those the same thing, constructing a world where gods control the weather, versus, given that we now accept that the gods control the weather, that it's Poseidon who must be angry because it was a flood? And I'm having trouble understanding how this fairly rickety, weak framework can explain something as rich as positing that gods control things, and then the situation where it's now flooding in Athens, most likely it's Poseidon that's angry, not Zeus. They just don't seem to be the same to me. That's what I'm in trouble.
So I think they're different in the sense that you're manipulating different kinds of knowledge, right? So like I can intuit what you mean when you say, Poseidon is angry, right? But like, we don't have formalisms yet that can encode that level.
But that's what the whole problem is. But that's the whole problem of human cognition.
Well, I think it's a large part of a large part of the problem of human cognition, but it's not the whole part.
Well, I'm just, again, I'm genuinely asking. I do not have an opinion here. I just find myself feeling that it just can't get there, and I don't know why. It just doesn't seem enough to me, and I don't.
What doesn't seem enough?
That this framework of probabilistic programs is going to explain the reasoning that went on in terms of constructing gods as the explanation for the world, and then that moment of inference that Athens was flooded, it wasn't hit by lightning, therefore it must be Poseidon is more likely to have been who's angry. We're uncertain because we don't know what they're arguing about up on Olympus. So it could be Zeus deciding, because he's so powerful, to use water to get angry with, but it's most likely to be Poseidon, not Zeus. I can see that being somewhat Bayesian,
mm-hmm.
right? But it just doesn't do the heavy lifting of thinking about gods being angry and these constructions. It seems like a turnkey thing that can be used almost metaphorically, but it just doesn't seem to be the thing itself. And I'm happy to be corrected.
So, I'm in agreement that a large part of the problem is how we represent knowledge. In some sense, my talk, a large part of it was saying that there's a large fraction of the kinds of things that we can do, not just Galileo and so on, but we can do, which isn't captured. But I think a lot of it is, in the sense, in the degree to which it's not captured is in the degree to which we can represent knowledge about these things. And also, again, the kind of, taking the example that you just had, was very much, my kind of Galileo style proof proposal is very much in that paradigm. A lot of the arguments we make seem to follow this kind of step-by-step reasoning to come to some conclusions. And this is a little bit different from at least the implementation level of how Bayesian inference algorithms work and the conclusion. So I do think there is a lot missing, but it comes down to, at least in my opinion, how do we represent knowledge? What formalisms could really capture kind of the amazing diversity of things that we can encode and talk about freely and communicate? You know, I could easily understand your story, even if I don't know kind of Greek mythology, right? How can we have representations which capture that? I think that's a hard thing to do. But I don't think its hardness obviates, or maybe not negates, kind of the expressive power of universal probabilistic programming languages, which can encode a lot of things about the world, even if they can't encode everything about the world.
John, you're muted.
Probably a good thing. No, I'm just struggling with, you know, it gets down to this Marian thing. Are we really talking about some process under the level of awareness that then in its final stage becomes expressed in language, but really what you were doing was some kind of probabilistic inference, which finally just gets read out with words like Poseidon and Zeus and Agri, and that's really just the icing on the cake, and really underneath is this probabilistic inference. And that's really what's happening, or whether that's a metaphor for what's happening. I just can't quite decide between those two things. And it may just be a cognitive deficit on my part that it just doesn't click, as in, voila, we're there, we've got this worked out. And I don't think it's just because we don't know the nature of the representations of knowledge upon which to do this probabilistic inference. It doesn't seem like that's enough to go, oh, so in other words, we've solved the general reasoning issue, it's this probabilistic inference, now we need to separately solve the representation issue, and then at some point they'll fuse and we'll have the whole shebang. It doesn't quite work for me, but it may be true. I'm just struggling with it.
And John, I just want to say, so while I'm sympathetic to a lot of the things that you're saying with regards to sort of maybe the current state of models, I wonder whether you just think this about any computational model. It seems like sometimes I get the air that it doesn't matter if it's Zenna's model or my model or Melanie's model. It's just like computational model, you find that hard to accept as a bedrock for the rest of the things that are happening. I worry, how much do you think that's the lack of satisfaction, and how much do you think it's specific to Zenna's approach? And in the meantime, I just want to add that Zenna's particular contribution seems like it is moving towards what you're saying. It is bridging at least one kind of model to the kind of more higher level, language level approaches that I think you might like. So that's why I'm a little...
No, I'm not. It's not some deep-seated childhood trauma when I ran into a computational model and it abused me. I'm just saying that it's a little bit like, you know, I've seen Roger Penrose many times say that he doesn't think intuitive thinking is algorithmic at all. So in other words, all I'm saying is that this is a broader, again, it gets to this system one, system two difference. I think that a lot of things like guessing the position of your arm in space, and there's uncertainty about where your arm is in space, and you estimate it based on using your proprioceptive and vision, and they have different degrees of certainty associated with them, and you integrate them in a Bayesian optimal way. And we do that without having any awareness. In fact, it's very interesting that verbal report of position of limb and where you actually know your limb is with respect to your next move are dissociate. It's very interesting that verbal report of limb position and what you actually think, where you think your limb is, dissociate. So in other words, I have no problem that this is going on, you know, subpersonally. Where I'm having trouble is when personal overt meanings play such a huge role in reasoning, how to put it back into this subpersonal computation. It's just something that I struggle with. And it's not because I have anything against computation.
No,
I've used them myself for decades. It's just that I just don't find this fusion is clicking for me yet, but I'm more than willing to have it explained to me.
Yeah, so is it a fair summary of what you just said, that you're less comfortable with computational models that claim they are capturing something that you would consider system two? You're muted.
Yes, I have trouble separating out thinking about Poseidon and Zeus and gods and floods and the subpersonal processes that we are inferring are doing those things, I think that's a mystery that all these fields are struggling with, and I don't think that it can be subsumed in any way. But I'm genuinely being honest about my puzzlement. It's not because I have a strong opinion about it.
What if the same way that we give words to objects in the world, we gave words to internal states that are not just emotional states, but thought states, right? So internal representations of things. And then one word for the same way that a quote that Zenna was showing, I think Kepler was like some spiritual force or some other kind of force. He knew he could infer there is some kind of force. He couldn't name it. He was like, it's some kind of force. I don't know what it is. So it's a spiritual or some other kind, right? There is some representation of what's happening in a stellar system. And there is some mental process that says something should be here. He doesn't have an explanation for it. He gives it a name. Years later, scientists figure things out a little bit more with less spiritual words. But it seems to me that it's less magical if you just think about the internal representations as nameable, as objects that are outside of you. And then whatever reasoning that can happen, whether it's about I'm picking up this glass and I'm taking it here and I'm passing this glass to you, you can't receive it because you're in a screen. Likewise, the reasoning that I just used linguistically or verbally could be applied to some internal representations. And so
I guess what I see what you're saying, Ida. I guess what I'm saying is that, we're the only animals that name anything, right? So in other words, all I'm saying is that this framework, I think, would work, for example, if a cat is going to decide whether to go under a wall that's beginning to fall. It may make some sort of inference that it's going to get through in time before the wall falls, or it won't, and it takes another route. I think that one could come up with this framework. I just don't think it's obvious to me how that framework of a cat deciding whether or not to go under a falling wall, which obviously seems to be some kind of inference based on some sort of uncertainty, it just doesn't seem to be the same thing to me once you're talking about Poseidon and Zeus. I just don't see how the everything comes under it. It begins to feel too thin a theory for it.
What do you think is the salient properties of the Zeus example?
Also, just one moment. So after this, I would like Josh to speak because we have the guests on screen, but we haven't.
Well, one is completely saturated with meaning. The one with the cat under the wall has no meaning.
Okay. I agree, and we've spoken about this before. I agree that we aren't coming close, in our formal models to a notion of meaning, which is anything close to kind of a human notion of meaning. When you say Zeus was angry and that caused something else, right? The notion of anger, I have a rich conceptual structure around that, right? And so I agree that we are not capturing that in this formalism.
Josh,
but there is a way that metaphorically one could say, oh, Athens flooded, Poseidon controls water, Zeus controls thunderbolts. Therefore, it's more likely that if the gods are angry, that given it was a flood, it was Poseidon who's responsible. It sounds somewhat Bayesian. You're uncertain. You have a sense of what's more likely. It could well be that they're playing silly games up on Olympus and Poseidon pretends, Zeus pretends to be Poseidon, but it sounds Bayesian to me, right? I don't know how useful that is. To say that when you guessed it was Poseidon, not Zeus, because it was Athens flooding, forgetting what I asked before, which is the whole notion of inventing gods that control weather and blah, blah, blah. It's at that stage, it just feels a bit thin. That's all I'm saying.
I think it's still useful because you have to think of the alternative, right? Which is that you start to conclude things which have no basis in plausibility. So I think it only sounds thin because you're taking it for granted.
But to de-thin it, you had to use the word plausibility. And plausibility seems to be something extra than just integrating sources of uncertain information.
I mean, yeah, I think, just to restate, I think a large chunk of kind of your contention, at least in my opinion, does fall under representations of knowledge, which I'm very happy to accept, do not capture the kinds of examples that you are suggesting.
Fascinating. But anyway, I will say no more because I'm just being annoying. Okay, thanks, Zenna. Bye.
So I guess you were asking me to speak. I can jump in a little bit. Yeah, I mean, it's very interesting listening to you guys debate here. The mute button was very useful for me. So let me just listen. I think the interesting things to debate and discuss really are not really the points of disagreement. I mean, as I said in the chat, I would certainly be one of the first people to defend the value of Bayesian models of cognition and accounts of certain things that the brain does. But in my own work, and I think in my colleagues and in Zenna's work here, the interesting thing is what is missing, what you don't have, just by thinking in terms of probabilistic inference. The kind of within paradigm approach that Zen is pursuing, that is often what I've pursued also, is to say, what can you add to the principles of probabilistic modeling and inference that aren't there, in like what traditional, say, excuse me, Bayesian statisticians have done, but that we would need to move us closer towards an account of human reasoning, right? I don't think we're very close to it. I think it's so interesting because we're not that close to it. I don't think there's any better, I agree with Zen. I don't think there's any better proposal on offer for the kinds of cases that he's talking about. And so I think one valid strategy is to take what does work for, say, as we've all sort of worked in the sensory motor domain and some of the kind of, the aspects of cognition that are shared between humans and many other animals that are more in the here and now, and to say, well, we know that our brain does that, and there's good reasons to think that it does it as some kind of approximation to probabilistic inference, at least at some level of abstraction. And then how do you get from there to a theory of cognition? You could just bring in some totally other account, but it makes pragmatic sense. It's not ideological. It's just a purely pragmatic idea that to explore what you can add to that. So the idea of representations of probabilistic models as probabilistic programs that let you capture these ideas of like imagining what things might look like under different lighting conditions and different surface properties, so the representational power of these universal probabilistic programs, and then the ability to do inference within those and comparing between those. That's a good step forward. I think we should all agree about that. And this other idea, which I think is really intriguing, that you could have something that was like a proof or have kinds of reasoning about the structure of a program, or the structure in particular of a probabilistic model when it's formulated as a program, where we can use tools from the programming languages field for reasoning about the validity of a program or its logical structure. That's also really interesting, and that might start to capture some aspects of scientific thinking and scientific argumentation and communication. So I think those are several interesting ideas that move us in this direction. But things like the questions of where do our cultural narratives come from, how do we come to the idea of gods, and so on. I think those are also really interesting questions. But I don't see Zenna trying to answer those. Mm-hmm. I mean, I don't think we should debate those here. I don't think anybody has a good answer to that, or at least it's not within this toolkit. It's going to look to, I won't try to speculate here, although if you want to, we could. But, I think one of the things that's so interesting about these scientific discovery cases, like what Galileo was doing, what Kepler was doing, right, is that they're somewhere in between, or they have some properties in common with perception and other things in common with these other, much more, whatever you want to call them, higher, more abstract human things. They have become part of our cultural narrative of science, as Zenna said so beautifully at the beginning of this talk. So by studying those cases, I think we can make some progress in moving this paradigm towards, some account of how thinking works. But whether it's the stuff Zenna was talking about, or he highlighted Laura Schultz's work, which has been a big influence in my own work and Zenna's, a question there of like, how do you know, where do new ideas come from, as Laura has talked about? You know, she would be a great person to have in the Future Learning Salon and discuss that. You know, she's also used Bayesian models, but she would be one of the very first people to say, here's a thing that nobody has a good account of, whether you're Bayesian or anything else. Where do the hypotheses come from in the first place? And I think that's an incredibly good question. I think, as I said in the chat, I'll just say one more thing and then let other people talk. You know, I think this is a point of more agreement than anything else. Whether you're talking about sort of system 1, system 2, or perception and cognition, or why are some things, you know, what seem like the issues of tractability or intractability, it's worth considering the difference between the Galileo and the Kepler case, right? Galileo, you know, he, as Zenna argued, in a sense, as soon as he saw the data, which was what the moon looked like through this telescope, he knew that there were mountains on the moon in some sense, right? It then took him a little while to maybe formulate an argument, but the book Sidereus Nuncius, which Zenna talks about, you know, he basically just dashed that off. It was kind of like a grant report, like one of these things we write for our grant officers. He was writing to the Medici dukes, who were his sponsors. He was also, he was trying to avoid being scooped because other people were building telescopes. So it was like posting a preprint on Archive. It was, you know, he knew it right away, and he made an argument which was mostly visual. Kepler, in contrast, took many, many years. I don't remember exactly how long, but more than a decade, probably much longer, after he had the data to come up with the idea of ellipses. And ellipses, in some sense, it's you know, it also seems like an incredibly simple, compelling theory when you see it laid out, or at least, you know, it was enough to motivate other people like Newton to try to explain that and give a more, you know, kind of dynamical explanation and a more, in a sense, causal explanation, okay. Or general explanation. But those are interesting cases, right? Why did Galileo know it as soon as he saw it, and why did Kepler take many, many years? And one possibility is about the way perception works, right? And it's something about being able to see in such rich detail that, you know, the way the shape from shading problem effectively was unfolding before his eyes. But it's not enough to do that, because he also has to justify it to himself and then figure out how to explain it to other people. So it's not purely perception, it's something in between perception and cognition. Kepler also, you know, there's a perceptual component. I'm sure he drew pictures, I'm sure he plotted data in some form, but it wasn't, you know, the coming to ellipses as opposed to various kinds of circles and other things. I mean, in a sense, as Zenna didn't quite have time to talk about, he did a little bit, but, you know, if you read what Kepler wrote and his own mental imagination, in many ways, his perception and imaginative faculties were holding him back, because he was thinking of central motive forces and things that really lent themselves more to think like circles, that didn't quite fit with the mathematically, sort of statistically compelling account of an ellipse. With a very simple model fits the data really well. So anyway, I'm not saying this, we have full accounts of anything, and I don't think Zenna did too. I mean, again, I think he's just pointing the way towards an interesting set of things for us to think about at the intersection of, you know, philosophy and history of science, cognition, and what does it mean to think about reasoning in formal terms.
I had a question for you.
Oh, thanks. Just a very quick clarification thing. So Josh, there's absolutely no doubt that there is a lot of usefulness to the Bayesian approach and the probabilistic reasoning approach. So you said, oh, everyone agrees that it's useful. I 100% agree. I think everyone agrees. I think it's, and
the interesting questions are, what else might you need in order to develop this as an account of cognition, right?
Right. But another question also is, and I think that's the point of disagreement that I had with Zenna, or the pushback, which was that this is the approach. I think that there is a difference between this is a useful approach versus this is the approach.
Well, I don't think Zenna was arguing, or I wouldn't argue, that this was the approach. Were you, Zenna? I don't know. I think he was just saying, this is a compelling way to go, and there's an argument for why it's a compelling way to go. If somebody else wants to come up with another account of this, that would be really interesting, yeah. And then we should discuss that.
Yeah, right. No, we did pull back from that, but I think that there was a point, and that was the point where it's recorded.
Yeah.
But I think that was the point where I was doing the pushback. Otherwise, I 100% agree with you that it's a very useful approach, and that was just a tiny clarification.
So do you think? I know it's not necessarily the main thing that you were working on or thinking about, but do you think there's a better, or what's a good alternative one that we should consider if we want to explain, for example, how Galileo or Kepler came to their inferences?
That's a great question.
What would be a good alternative? I'd love to consider others, because I think they might have good ideas to offer, and the right answer is not going to be one that, certainly not any simple version of any standard model. I mean,
yeah, so I can tell you my sort of discomfort with this is the number of alternative hypotheses that are generated, and the way that we consider evidence for different hypotheses, based on just phenomenology of knowledge and how the process of science happens. So based on reading history and philosophy of science in various domains, because I don't know if you know that at some point I did a graduate degree in history and philosophy of science. I don't feel like the Bayesian approach really captures the reasoning process and data collection process that happens. And I think that's the part where I think that possibly cognition is...
I think we all agree with that. I mean, at least in especially in things that are like reasoning and scientific discovery. That's why Zenna is trying to, he's pushing it in several interesting ways that he just sketched. Or like what Laura has been talking about. She's also trying to challenge Bayesians or anybody else who believes in computational models of thought, right? So again, I think, the tradition, simple textbook models from Bayesian statistics are no more accounts of full human cognition than simple neural network models from the mid 80s either, right? And neural networks have made a lot of progress by incorporating all sorts of other ideas, and the same is true with probabilistic programming, right? I mean, like the ideas from programming languages and formal methods that have come into that have made, like, for example, the kind of formal counterfactual reasoning that Zenna was talking about possible. So again, I don't think we should have. I don't think we need to debate that. I think it's also interesting to think about. Again, I think it's interesting to look at these cases from the history of science, these particular ones, because they're beautiful and they have a lot of richness to them, but they're not that hard, actually. So they're not as complex. Like the questions of how Galileo came to what he was doing is I think more approachable, or how Kepler came to his models, or other inferences of Galileo, like how he figured out that the little dots he saw near Jupiter were not specks of dust on the telescope or stars nobody had seen before, but were other things that were kind of like little planets around planets, or moons of a planet that wasn't the Earth. Those kinds of examples are sort of sweet spots where we can push our understanding forward. And it's also, I guess, one more thing maybe we could add into the mix is, like, if you don't want to argue about the rhetoric of Bayes, is just think about what people do in statistics. I mean, I'm very inspired by Andrew Gelman's, for example, philosophy of being Bayesian. He's the author of one of the leading textbooks in Bayesian statistics, and one of the leading, like, probabilistic programming packages, and one of the co-inventors of STAN, which is very influential for probabilistic programming and statistics. He's not like an ideological Bayesian. He's a practical Bayesian. He's well aware of some of the issues that are not dealt with in the Bayesian paradigm. And I think we can say, look, this is really just about modeling. I'm trying to build models of the world. I want to understand how to assess what a model tells me and what it doesn't, and how to compare models with each other. And I like increasingly to move the toolkit towards one that either automates on the machine sense, or kind of increasingly computationalizes human thought processes that can take us towards how do we actually, build models, improve them, grow them, because that is what thinking does, and it is what science does. But I think all of us are aware that at least the classical Bayesian ideas in statistics don't do that, but they do provide a really good foundation for understanding what a model does, how it makes sense of data and handles uncertainty. And so what we're trying to do is say, what can we do to build on that, to take us towards where we're trying to go? It's one route up the mountain, and
they're different routes. Yeah,
they're different routes. Yeah.
Sorry, I believe in the computational approaches. It's just, as a functionalist, and I am no match in terms of seniority to you or John or Melanie, but the thing that makes a little bit, it feels a little hegemonic sometimes at some conferences. It begins to be like, it's this, or no.
Yeah. There's like imperialism or hegemony, and you see this in all paradigms, right? I mean, you can see this in some Bayesians, you can see this in some neural network people, some reinforcement learning people, and yeah, I mean, honestly, yeah. Thanks for pointing out my age and my seniority. The older I get, the more impatient I am with anybody who's hegemonic about anything, whether they're Bayesian or anyone else. So I can share that with you.
Awesome. Yeah, the whole point was, okay, and I just want to highlight before John starts, just want to highlight I was impressed with the movement that Zenna had made from remaining in that Bayesian to a place that's a little more higher level of explanation. And I think that that's an interesting move that we didn't, I think it didn't get the credit as much maybe.
Well, yeah, I mean, Zenna is one of the leaders in probabilistic programs and probabilistic programming as a way to think about AI, and he doesn't call himself a cognitive scientist, but okay, I would call him a cognitive scientist.
Okay,
I think that's an exciting. I mean, I do give Zenna some beautiful work there, and I love this work he's doing here too. But he's not the only one. I mean, that's a development in the field. That's somebody in the chat mentioned Noah Goodman's probabilistic language of thought. Vikash Mansinga at MIT is also doing that kind of work in his probabilistic computing group. A number of others. I think. It's another person I mentioned is Kevin Ellis, who works with Melanie and me and is a recent graduate from our group. He's done really cool things connecting programming languages, program synthesis, Bayes, and neural networks. So there's like a lot of actually really interesting motion from within people who are using probabilistic inference tools towards higher level abstractions in their models. And probabilistic programs is just sort of a name for that. One name for that class of approaches, which is, I think, going to be increasingly valuable.
I had a question, Zenna, Joshua. The word inference, a lot of people in propositional logic use the word inference, right? And it seemed to me that a little bit of what I saw in the programs looked like either or logical thinking. And then there's the inference that you can assume that your nervous system is doing about where is your hand in space, but you would never necessarily couch that in overt propositional logic language. And it just seems to me that what's being conflated in the Kepler and Galileo stories is, as you yourself, Josh, said with Galileo, as soon as he saw the bumpy surface of the moon, well, that's logically no longer compatible with a smooth surface, right? In other words, there's a difference.
He didn't literally see the. I mean, you want to talk about what's literally a metaphor? He didn't literally see the bumpy surface. I mean, he saw an image that his visual system interpreted as a bumpy surface.
Sure, but we're not talking about perception. Yeah. Okay. Well, we're not talking about perception. We're not talking about probabilistic perception. We're talking about, let's say that he had a perfect telescope and saw it was bumpy.
But he would still.
I mean, so in other words, it seems to me that you're conflating logical proposition forms of inference based on overt knowledge and definitions with saying that your nervous system is inferring the position of your arm based on some optimal Bayesian integration of sources of sensory information. Those seem to me qualitatively different.
Well, I don't think I was conflating those things. In some sense, I had explicitly separated those things. I mean, I think, to your point, even if you had a perfect telescope, you'd still have to infer the structure of the moon because, you don't see in 3D, you see in 2D and you infer 3D.
We're not talking about that, right?
Well, but it's an important part of your argument, right? Because I think that seeing of the moon and inferring the 3D structure isn't so different from, perceiving where your arm may be in three-dimensional space. You have some model that may be a low-level kind of perceptual or proprioceptual model, and you can make inferences in it. So I'm not claiming that propositional step-by-step reasoning is the same thing as perceptual reasoning. So
what's the difference? What's the qualitative difference?
Well, I think there's two differences, and I think I've highlighted both of them. So one difference is what kind of models and knowledge you have. And the other difference is part of what I was saying in my talk. These argument style reasonings are a different kind of thing than the kinds of inference procedures that we use in probabilistic programming languages, right. Or we have used for a long time to draw samples or to get to some conclusions that way. So it's a different kind of reasoning. It's a different object, right? A different mathematical object, different conceptual object. Sometimes it can give you the same result. You can come to a
right, and that
plausible
different object,
conclusion.
what I would maintain is that different object is really what Kepler and Galileo were doing.
Well,
That's what Zenna was saying.
Right. I mean, I think in Galileo's case, my guess is that, like Josh said, he saw the moon, realized it was bumpy, and had to justify it both to himself and to the people that he communicated. Like, he couldn't just see the moon and then, communicate that through mind transfer to everybody else, right? He had to put it into an argument form. And that's a different kind of construction, right? And I think it's interesting that in math, we have constructions which seem to capture some of that. And I think another funny thing is that, in some sense, Aristotle, Kepler, and so on, are the kind of repudiation of Aristotle, right? Like the getting rid of this kind of Telemetric Aristotelian model. But in some sense, Aristotle still wins because he's the one who devised kind of the rules of logical reasoning, right? Or at least he distilled them into some form. So I kind of think of it as like Aristotle's revenge is what we should do.
I can't help but mention one of my favorite examples of early Bayesian inference, also from Aristotle, because I think it also, I'd love to hear what you think about this, John, because in some sense it helps to address what you're saying. So Aristotle had very different ideas about the heavens than we did, but in his writings on the heavens, he made an argument, which as far as I know, I'm not an expert on this, but it's the earliest example of a kind, I would call it a structurally Bayesian argument about what was going on outside the Earth. He said, how do we know that all the stars are fixed to a single crystal sphere that rotates around the Earth, as opposed to the planets, which each follow their own mechanism? They're not all on a single sphere. Well, of course, he was wrong about the stars being fixed to a crystal sphere. That's not what we currently think. But he made an argument, which in some sense is kind of morally right, which is he said, well, look at the stars. Over the course of a night, they all move along paths, but what paths do they follow? They all follow circles, and those circles are concentric. They have a common center, and the ones that are further out move faster, and the ones that are closer move slower. That I'm not getting his words exactly right, but that would have been a huge coincidence if they were all moving on separate mechanisms, but is exactly what you'd expect if they were all in a single crystal sphere. So therefore, because nature abhors coincidences, that's the best explanation. So he made an inference to the best explanation within his paradigm. That, I think of this as like your Zeus Poseidon example, but he was in the same domain of phenomena that Kepler, Galileo, and Copernicus and so on were reasoning about. He had the wrong paradigm, the wrong kind of mechanistic model, but he made kind of the right structural inference. In this case, we would say, well, it's because it's the Earth that's spinning rather than the stars spinning, but there's a common cause to the star's motion, in not the same way that there is for the planets, at least relative to Earth and so on. So, again, I think that these kinds of examples, they lay bare a little bit the structure of human thinking and the ways in which it has components of probabilistic inference, while also pointing us towards some of the things that are missing and needed for this or any computational paradigm for reasoning to go towards.
Yes, it is fascinating, this mixture of what seems very much probabilistic inference and then this logical argumentation that is also done, right? Which is, and as we know, one form seems to be this probabilistic inference and the other one seems to be this logical argumentation. And it seems to me that those are different beasts, and we don't have as much of a bead on the neuroscience of the logical argumentation as we do maybe on certain examples of.
Yeah, but I think that's where Zenna is trying to take us towards, at least the computational cognitive science of that, and maybe ultimately the neuroscience of that. And as he said at the beginning, he's taking advantage of the fact that this is Salon to tell you about very, very recent work that is just starting to take shape. So I should just say, I'm going to have to get going pretty soon. I'm going to quiet myself now and happily listen to what others are saying. But if I disappear, I'll just say thank you so much for inviting me into discussion. I have only learned about the Learning Salon from Zenna when he invited me to come to the talk here. I think it's great. I'll try to come to others. It's really an awesome community and great set of talks that you've had here. So thanks for letting me participate.
Thank you, Josh.
Good to have you again.
Melanie, you've been waiting so patiently. I think you can ask a question.
Hi, Melanie.
Yeah.
Hi. Zenna, thank you for this. It's really interesting talk and discussion. So this is in the same vein as the John's question about like metaphorical versus sort of actual use of these ideas. But I'm going to move away from Bayesian reasoning to the notion of programs as kind of concepts. And I want to probe you as to how sort of literally do you mean, like Copernicus had a program in his mind when he was thinking about these issues? I think you had a little slide with Copernicus having a program. Or is a program just kind of a metaphor for a general sort of internal model that's useful in machines, but not something that people literally represent?
Yeah, good question. Yes, I think it comes down to how literal you want to be about programs. So maybe I would claim it, make the claim slightly differently, which is that I think whatever we literally have has to have some of the structural properties of programs. They're obviously going to be very different in the ways, right? We're running on different hardware, but I think there are just some key ingredients which whatever representation we have to represent theories must adhere to. And these are, many of these are linguistic in the sense that we have composition, we can combine different theories together. I think it has to have a notion of a computation, right? Which is why I'm using the term program as opposed to just a linguistic expression. It has to be able to express, represent uncertainty. You have to be able to express, the kind of, the laws which people say. So I think if you just go through and systematically look at what are the components of these theories as stated by the people who have said them, you end up with something which very much resembles a program. And another way to think about it is that if I want to actually simulate these things, right, then I have to encode them as a program. So I think there's kind of stronger and weaker claims. Like the weakest claim is that these models have to include some kind of computation, but the stronger claim is that I think they have to incorporate a lot of the features that we've built into our programming languages, right? Well, another way to think about it is like, why do our programming languages look the way that they look like? It's because we've designed them to be able to model the world, right? Why do they have objects and classes and functions and types, right? And assertions, because we need these things to model the world. So I kind of think of it as programs are kind of engineering response to be able to model the world in kind of the best way we have done so far. I think our actual representations will be very different in many regards, but I think there are going to be some fundamentally kind of shared similarities.
Well, let me just follow up on that. So I've been reading this great book by Matthew Cobb called The Idea of the Brain, and he talks a lot about sort of the history of people thinking about the brain in terms of analogies with current technology, whatever that happens to be, like, telephone switching networks, sort of early computers, parallel computers. And these analogies have been both useful and also somewhat limiting because they kind of limit our thinking to a particular paradigm. Like, the brain is a computer, right? And I'm wondering, this idea of programming, it's very convenient that programming is something we all do all day. And we're also sort of making this analogy between programming and concepts, like a program is a concept. And I know that you and others in Josh's group have talked about sort of the game engine idea as kind of an analogy with a video game engine and our reasoning systems, our perceptual systems, and these seem to fit in this idea of using analogies with sort of our current technologies to conceptualize what's going on in the brain. And I'm wondering, are these useful analogies? Are they limiting analogies? Have you thought about that at all?
So yeah, I think there's a real risk of what you said in the sense of taking the framework you have and kind of imposing that upon reality, right? So I agree that's a risk. Again, I think of it from maybe a few different routes. So one is going back to, the ice cream example that I said earlier on at the start of this talk, right? How did I know that the sound of the clang on the floor was the cause of the spoon in another room that I couldn't see. For me, the only paradigm that could explain that maybe not the only paradigm, but the one in which I find most compelling, which can give a pretty concise, intuitive answer and can actually work, we can actually build machines that do it, is to incorporate that knowledge through a simulation, which is a program. And so I come from somewhat from a functional perspective in that sense, which I don't find any other paradigms coming close to being able to capture that kind of active reasoning. And if there is one, I'd like to know about it. But I think you can go from the fact that, again, looking at outside of artificial intelligence and reasoning and AI, we build simulations using programs. We don't build them out of kind of pipes or any of the other analogies that we've used to describe in the past. We build them out of this machinery, computation. So there is something fundamental about computation, which is not just one other thing in some sea of possibilities that we could use as analogies. That said, I do think there are many structural differences between programs as incorporated in a current state of the art. After all, we've only been programming for 80 years or so, give or take, right? So things are obviously going to change, but there are going to be some core fundamentals that persist, like the notion of computation, the notion of universal computation, the notion of a function, right? So I think there are going to be some constants which remain throughout time as we develop our conceptual frameworks for modeling the mind.
And just a little comment on that, Melanie, the Matthew Cobb book is very good fun to read, but it goes completely off the rails with an analogy argument when it comes to computation. I agree completely with Zenna. You simply cannot do without the notion of computation. And actually, one of the fascinating things about computer science is and as David has spoken about a lot, there's a very deep notion that computers have taught us about computation and substrate independence and the difference between hardware and software. So this idea that you can get away with these notions and just fob them off as just our current day hydraulics is severely misguided in my view.
Thanks for the question.
Thanks.
Hi.
Hi.
Yeah, so I had a question about how philosophers talk about inference. So they'll distinguish between inductive inference, deductive inference, or abductive inference. Mm-hmm. So yeah, I only learned about kind of abductive inference recently, so maybe other people don't know about it. So maybe I'll just try to summarize. Like inductive inference would be kind of from many observations of black ravens, you conclude that all ravens are black. And some deductive inference, you can make this kind of logical deduction from premises to some true conclusion. But then abductive inference is supposed to be this a separate type of inference that's not quite like either of the others. That seems to be what scientists do when they arbitrate between different theories. So you don't have like direct observations in the same way that you do have with inductive inference, but you're, people, this has already been kind of implicit in the conversation, so I'm just kind of being explicit about it. So abductive inference being kind of inference to the best explanation. So I was recently having a conversation with a philosopher, Trey Boone, and he was asking me about kind of machine learning and what kind of inferences are machine learning models making. And I hadn't really considered it, I wasn't really sure, but yeah, so I wanted to ask you, like, do you think that kind of are these useful characterizations kind of first for thinking about building machines that can reason? And the types of reasoning that we want to endow kind of machines with, is it particularly abductive reasoning? Like you've been focusing on these scientific examples. Do you think that kind of the, artificial systems we already have, are they doing inductive inference mostly, or yeah, maybe I'll stop there.
Yeah. So just to clarify, when you say, do I find these useful, did you mean the delineation between inductive and abductive and deductive, right? I see. Yeah. So I think people have different opinions and beliefs about this. My personal stance is that deductive reasoning is a thing, and inductive reasoning is a thing, and abductive reasoning is really just inductive reasoning on a different representation. So, what is deductive reasoning is pretty straightforward, right? You have kind of deductive conclusions. It's what you do in mathematics. You build proofs, right? Inductive reasoning, kind of the best or the most prominent formalization of that is probabilistic inference, right? The conclusions aren't deductively implied by the premises, and so I need some way to handle the multiple possibilities. And so probabilistic inference or probabilistic modeling, or just the rules of probability, give a framework for inductive reasoning. So where does abductive reasoning fit into this? Well, again, I think you could do it in different ways. Either one, you could call it a different style of reasoning, or my preferred way is to say, actually, it's just inductive reasoning over the space of theories, right? Because you don't know what the true theory is, but you have to infer what it is. And I think, why is that a good way to think about it? And in my opinion, well, at least in the framework that I work in, that's what it literally is. I can construct a prior distribution over different theories, and I can do probabilistic inference, which I would call inductive inference, over that space of theories. Now, going back to the discussion earlier, you may want to do, use different approaches to do inference in the space of theories versus the space of, kind of values within a theory. But I don't think you need a fundamentally different style of reasoning, right? There's no set of new rules that I can go to for abductive reasoning. And so that's my stance. I think there'll probably be some people who fiercely disagree, right? But I think it's, the real distinction is about what are you doing inference, inductive inference over, and you can call some of that abductive if it applies to a particular case. I think just as an additional comment, sometimes people think about, they say abductive inference is constructing explanations of things, right? And I think that is a different kind of thing. I think the construction of explanations is not fully within the framework of probabilistic inference. Now you have to start thinking about causality. It's a kind of a whole different beast, actually.
Can we just clarify that a minute? I mean, I think Jessica asked her question, and it seemed to me, I find it a little odd to call induction probabilistic inference. I mean, is it really what happened when, the action potential was shown to, the mechanism was shown in the squid giant axon, and the assumption was made that all axons do that? I don't see quite why that's probabilistic inference. When it comes to abductive inference, it is about explanations, right? An example I just read about very recently is two people have a fight and they vow never to speak to each other again. Mm-hmm. And then they're spotted at a movie together, right? And then you have to go, well, what on earth happened there? Were they forced at gunpoint to sit next to each other? Was it so dark in the cinema that they didn't realize they were sitting next to each other? Did they make up? Are they doing this for their families? Mm-hmm. Right? And the thing is that we do come up with an explanation very fast of what's most likely to be the explanation that they're sitting next to each other after they ostensibly had a fight. Okay, now that is what abductive inference is. And as you said, I do not see how talking about probability inference is going to help us there, quite frankly. And also with respect to induction, I mean, isn't, the Ravens example, how is that probabilistic inference? In other words, if you spend your life, I'm just trying to understand, abductive inference without the explanation part seems closer to what you were doing than induction, right? I'm actually puzzled by what you said. I thought, Jessica, you were implying also that he sounded more like abductive inference, right? Did you think that it sounded like induction to you?
Well, I guess I thought that maybe the goal is to mimic sort of the behaviors of abductive reasoning in humans.
Right.
It wasn't saying necessarily anything about the mechanisms or algorithms that are going to accomplish that, but if we can think of it as a specification of behavior as kind of analyzed by philosophers then.
Yeah, but you are saying it sounded like we were trying to get to abductive inference, but now we're being told, Zenna, you're telling us that it's just induction that you're trying to make.
Okay, so if you see a bunch of ravens and you conclude that all ravens, which example? All ravens are black, right? So you see a bunch of ravens, black ravens, and you conclude that all ravens are black. The question is, how have you come to this conclusion? Right? Have you appealed to some special law just about ravens, right? Or do you have some machinery that allows you to take into account different possible kind of, theories about ravens, and you've concluded which is the most likely? So for me, the real fundamental technical distinction comes down between deductive inference and inductive inference, and everything else is really about what you are doing inference over. What are the kinds of things you are concluding? Are you making claims about theories? Are you making claims about particular instances? But for me, that gets into the representational part. Now, I know people will disagree with that, but I don't see it as a fundamentally different style of reasoning. I see it as a reasoning over a different type of thing. And there's very few cases where you can say, okay, I've seen five black ravens, and now I know deductively that the ravens are all black. I have to make an inductive argument, and for me, the most compelling, as we've spoken about already, paradigm for doing that is to use probabilistic inference. But you could do it, in other frameworks, but it's going to be an inductive kind of argument.
Yeah, thanks. That makes sense. I think there's probably lots of people who would agree with you that abductive inference isn't a thing. Yeah, maybe just I'll follow up again quickly, and that my last comment was just kind of a silly observation that if we're scientists trying to understand human reasoning, which we're modeling as scientists doing inference, it starts to feel like it's scientists all the way down. We have in cognitive development, we talk about the child as scientist model of how children learn to kind of understand the world. Yeah, I don't know. It just kind of is a funny observation, not really a question.
Yeah. Well, the person after you, next, Julian, knows all about recursive models of cognition, so he could probably better answer than I could answer. But you'd hope that somewhere your recursion would stop and you wouldn't just have scientists upon scientists upon scientists.
Thanks a lot.
Thank you.
Yeah, so I won't answer that question, but I had a question about this idea of using the kind of Copernican revolution as an inspiration. It seems to me that I guess my question is, if we buy the whole Bayesian inference thing, there's a question of what are we actually doing Bayesian inference over? And to make this concrete, if you think of Galileo, when Galileo was asking, okay, how is it, what acceleration are objects under when you drop them? All of the data that existed there suggested that objects don't actually fall, they're not subject to the same acceleration, and they hit the ground at different points, right? And what historians of science will usually tell you is Galileo's insight was that he decided to ignore the data. If Galileo would just take any two objects and drop them and try to measure which one falls first, he could have spent his whole life getting these measurements and never actually getting to the fundamental principle. And instead what he did was basically say, I'm just gonna ignore all of this data, which in many ways seems like an anti-Bayesian thing. He said, I'm not gonna worry about any data that we have. I'm just gonna try to think what's an abstract model where I can forget about all these variables like gravity and friction and error and all of these things. And then once I have these really simple model, let me figure what principle can I use to explain that. And it seems to me that as scientists, we do that a lot. As cognitive scientists, we build toy models to get these insights. But there's no data in there, right? It seems like the criteria that we use is something more like explanatory power and simplicity, and it's not so much about trying to, it seems like explaining, one thing that Galileo did was explaining data as a secondary step, So yeah, I mean, I'm just basically curious, like, what do you think about that?
Yeah, that's a good question. I don't really know the answer to that question. I would say that I think we shouldn't always use the term data in a reductive way, like just measurements, right? You have knowledge about the world. And I don't know how Galileo came to his theory of acceleration, but it was probably, as you're saying, some kind of consistency with his existing knowledge, right? Does this make sense with the things that I know? And I'm not going to, I'm not sure I'm going to claim this comes under the framework of Bayesian inference or probabilistic inference, but I think it does come under the framework of reasoning with the kind of knowledge that we have. And I think what's missing is that we really don't know how to represent the kind of the diversity of different sources of knowledge and information that guided the model that Galileo ultimately built to conclude that, whatever he concluded. So that's not, it's kind of a non-answer because I don't really know. I don't really know how he did it, but I do know that it seemed to rely on different kinds of knowledge and different kinds of models. David Deutsch has this book, which I think you've read, right? This, I forget the title. It's like Towards the End of Infinity. Yeah, right. Where he talks about the fact that we have, a whole space of different models, and we evaluate models and how they kind of how changeable they are relative to all the knowledge that we have. And you see this in a lot of talks. Not a lot of talks, a lot of work. The idea that we evaluate how kind of a model or a piece of knowledge is consistent with a wider web or framework of knowledge. And this kind of notion of a framework or a web or a network of knowledge is something that has not been captured or formalized in anything that I know about. And I think it would be necessary to get to the kinds of reasoning that you're talking about with Galileo.
Yeah, you said that was a non-answer, but I feel like that was a good answer. It reminds me of, Josh Rule's idea of like the child as a hacker, of like model building, where, kind of like echoing what you said, like data is not necessarily just the empirical data. Like, it seems like I'm just thinking, like, I think we also have like some kind of prior, of course, that like there's some simplicity in the world. There's some kind of Occam's razor that does reflect like not just an assumption about like, that cognitively we think simple things, but we actually think that there's like some simple structure in the world. Mm-hmm. And a good theory should be able to capture that belief that we have about the world. But yeah.
Mm-hmm. Cool. Thanks for the question.
It gets to the point that, was bugging me from the beginning, that it seems to me that there's an implicit way that you can operate on real continuous data versus now extending the notion of data to idiosyncratic knowledge. It seems slightly problematic to me again. In other words, it's very interesting what Julian was just saying, that sometimes a scientist can stumble across a truth not because of their trying to compare models against data, just like people can come up with the idea that the weather is controlled by Poseidon and the sun is controlled by Zeus. Who knows where that explanation for the world came from? You wouldn't call it scientific, but maybe sometimes wherever that kind of explanation comes from, which must be based on some kind of knowledge, right? Maybe what scientists do, in other words, scientists do something like that isn't necessarily data facing always, right? In other words, you can have a religious thinking approach that gets you to something that's true.
Right.
And what does one say then? That they ended up being right, even though they took a very religious-like thinking path to get there.
I mean, right? Kepler is famous for this. A lot of Kepler's insights from religion. His books are full of analogies, which he used to get to the truth in some sense.
But it seems a little bit different to a Bayesian update rule based on real evidence.
Well, again, I think, I don't know, I feel like the term Bayesian has a heavy connotation. For me, again, like Bayesianism is just about reasoning with incomplete information. And not much.
It becomes so weak that it.
But it's not that weak, because there are ways to reason which are inconsistent with that. right? And so going to what I said with Julian, I don't think of data as just, okay, we've got some numerical measurements, right? There's knowledge. A lot of what we do, it doesn't have numerical measurements at all. We have knowledge about how the world works. We have factual things that we've told each other. These are not, points in a table. And so I absolutely agree that we have to be able to incorporate that knowledge into our systems for reasoning. All I'm saying is that you need some mechanism to reason with that system. And, we could do that in a bunch of different ways. I think some of that will be Bayesian when we're dealing with incomplete information. But for me, the Bayesianism is the weakest part of this entire thing. I mean, I'm in complete agreement that we don't have the conceptual structures to formalize a lot of the kind of thinking that led to a lot of these examples. But we do have an increasingly compelling paradigm to capture some of it.
Can I follow up on that very quickly? And I apologize for keeping you guys wait, especially Andrew, you've been here for a while. So I think that you brought up also this challenge between representation and what we do with it, and the knowledge representation in particular, which is different from just a table of data. And so it needs to have particular structures, these representations, in order for them to be searchable within a given amount of time. Maybe they have a hierarchy, etc. So there are certain approaches that are really sort of focused on that. Do you think that there would be a complementary combination of different approaches for the Bayesian approach to have that? Or do you think there is already, and I'm genuinely asking this, a kind of an approach to integrate all of that? So, we know about sort of, some people do knowledge graphs. There are various versions that use particular aspects of probabilistic methods, but do you think there is a kind of a particular, and I know that you said that this is not a solved, you don't consider to be a solved issue in your approach, but what do you think is at least a couple of candidates for that kind of knowledge representation to integrate well with your sort of Bayesian approach?
Right. So again, my personal stance is to be as somewhat orthogonal or separated as I can knowledge from reasoning. I think in terms of knowledge, what could account for the kinds of things that we've spoken about. So I think you mentioned knowledge graphs. I think there's many compelling things about a knowledge graph, but they don't capture most things. So to give a concrete proposal, I think we need something like a hybrid of a knowledge graph and these programming languages. We need the ability to express the kind of knowledge that you have in a knowledge graph, like vast interconnected things, with the fact that some things are uncertain, with the fact that we want to be able to compute, simulate some things. So this is my vague way of saying, I do think there is a whole kind of path or avenue to explore representations of knowledge, and I think they would incorporate a lot of the good properties of the things that we have so far. I'm much more of a pluralist when it comes to knowledge representations than I am when it comes to reasoning. So
that's fair, but wouldn't you think the way that I reason will depend on what kind of structures my knowledge is stored as? So when you say they're orthogonal, I think that was a couple of us got surprised by that, and some people were mentioning that in the chat also. And the reason for that is, if I think about, if you give me a table of things, there are particular things I can do with it. If you give me an interconnected graph, there are particular things I can do with it. If you give me a hierarchical graphs, I can do particular things. So the kind of reasoning or inference that I would be able to do, how do I pull particular episodes, or do I only pull categories and abstracted knowledge? Do I remember any episodes at all? Like, what is my knowledge like? All of those things come into play with how I would reason.
Yeah, so I agree. So when I say this orthogonal, I guess I mean at the highest levels. To make an analogy, suppose that you had a bunch of different database systems, right? And they all had different implementations. And I did a query in one system. Like I said, let's select all the rows which have some date. And I did a query in another system, which had the same knowledge but different representations. If I got different results, I would think that something's wrong. Even though they might be using different algorithms, I would expect the same result, given that I've asked the same fundamental query. And so it's at this level
Actually, no. You know, that's how in the human memory research, we make inferences about what the structure of human memory is with the places where there is an error. You know, somebody comes and says, I think model A is the model of memory. And somebody else says, no, I think it's model B. So somebody else comes and designs a study where one of them will make an error. And then we see, okay, humans make that error, right? So I agree with you if we were only in the optimality domain, but when it comes to how do humans reason, for instance, I think we're in a different domain where indeed there is there are some particular structures of knowledge have limits. You can't do everything with them, you know?
Right. And also, I asked the same question that Ida just asked at the beginning of this, which is that some representations, especially overt ones, knowledge ones, are constructed with reasoning. That's how you construct those knowledge representations. So how come that then we're in a very chicken and egg situation. You seem to be arguing you have representations and then you do, you know, this universal operation on them, but the kind of representations that we're talking about here, you have to build out of reasoning.
So let me clarify. When I say orthogonal, I mean at the conceptual level. It's certainly true that when you implement these things, at least in a machine, you make lots of representation-specific choice. You tie your representation to your inference algorithm in a variety of different ways, right? My claim about the databases, I was talking about literal databases, not like human mind databases, right? All I'm saying is that the moment that you start doing reasoning with incomplete information, uncertain information, there's a question of like, what do you expect as the result? Like, what do I expect as the result of my reasoning? And you need some rules behind that. So that is, it's not a very strong claim. And you could realize that in different ways. But when I say Bayesian, I just mean probability, right? The rules of probability. And so if you deviate from that, which you could do in different ways, but there will be consequences, right? And in the sense that you might deviate, you'll pay some cost, or maybe you'll get that cost back, through some other gain in efficiency or something else, right? But the rules of probability exist for a reason, right? They're not just plucked out of nowhere.
So just to bring it back, so totally correct. I think the question was around the claim of orthogonality. Again, not about challenging the Bayesian approach, just the orthogonality of reasoning and knowledge, right?
Right. So that orthogonality is, I guess, the conceptual framework in which I work. I think when you actually implement things, you're going to see a lot of tie-in, as you said, on one data structure, some things can be efficient. On the different data structure, they can be inefficient. There are lots of representation-specific choices which make a real practical difference. I'm not in any way disputing that, right? I think that's true in both machines and biological brains and minds and so on. So.
Cool. This has been a very interesting talk and awesome discussion. I had a question, but maybe I'll ask something slightly different here based on sort of what's been talked about since, which is like, just to try to narrow down on what you're really trying to say with your theory here. Do you think that like GPT-3 is a candidate Bayesian model for doing some of the kinds of inference that you're thinking about, Bayesian probabilistic program model?
Sorry, could you say that again? I didn't quite understand.
Do you think that like a large language model is, well, let's first ask if it's Bayesian. Do you think that's Bayesian? Because it's, it's getting some data, there's some uncertainty because it doesn't get out, all the text yet. And it's trying to predict sort of like, what's the next thing you're going to say, let's say. Is that like a Bayesian process there because it's probabilistic with some uncertainty and it's generating, a probability distribution over like next things you might say?
I mean, it's hard to it's hard to answer that because literally what GPT-3 does is gives you the next, it samples a token, samples some words conditional on the previous words, right? So the question of is it Bayesian or not, like at what level? Is it like if you ask it a question, if you say, hey, GPT-3, give it some riddle in text, does it give you a Bayesian answer? I don't know. You have to probe GPT-3 to figure out if that's true or not.
Yeah, so I guess where I'm going with this, and it's kind of related to some of the earlier discussion, is that like, I can train a model to like listen to a, story about, like, to get some facts, some data, and to generate an explanation for that, right? And I could have this, like, transformer style model as a candidate model of how humans do scientific inferences, right? It's like they have some facts, they incorporate those with knowledge about sort of the larger structure of the world, which is learned over a long time scale in their weights, and knowledge about the particular data they want to explain in question right now, which is like the sort of story that they're getting right now. The like sequence of like statements or facts or whatever that they get as observations. And they're trying to predict something like an explanation. And, this is something that these transformer style models are increasingly good at. And I guess I'm asking, like, if that was my candidate model of how humans do scientific inferences, not that I'm saying it is, but if it were, would you think of that as being an implementation of your framework, or would you think of that as being something different?
So let me maybe answer in, well, you tell me if this answers your question. So I've played with GPT-3, and I've asked GPT-3, the kinds of questions that we could pose to the kinds of systems that I work on. So you can construct experiments where you say, okay, imagine a scenario where, I don't know, like a man, steps on a banana, and a moment later he was on the floor. Why was, what happened? What caused him to be on the floor? And, sometimes GPT-3 answers correctly in the sense of, say, well, he slipped on the banana, that's the cause, right? Or you can ask him questions about kind of you can ask it questions about plausible, outcomes. And sometimes it answers correctly, and sometimes it answers, strangely. So I think you have to distinguish between what GPT-3 is literally doing, which is predicting the next token, and what you can encode into that framework, right? And so the thing that was, admittedly surprising to me is that you can encode a lot of interesting things into this kind of predict the next token, and it's kind of amazing, right? But at the same time, it has no, it's not really trying to answer your question, really. It's trying to predict the next token. And so you can do prompt engineering to get it, to nudge it to kind of answer your question, but it's not based on any kind of semantic core, right? And so I guess I'm not sure, like, these days I don't bet against kind of large neural network models. I'm sure that they make them bigger and bigger, and they can do more impressive things. And you could conceivably be able to encode everything into these models. It's just not clear to me at the moment what they're actually doing. It will give you some result, but it's not clear that it's a coherent result. It will say two things which are contradictory, and so on and so on. So
yeah. I mean, so one point is I said GPT-3, but I also mentioned sort of summarization. Like, you can train these models to do various things. Next word or next byte pair prediction is a particularly dumb thing you can train these models to do, but it's easy to do at scale. Summarization and other things like that tend to get slightly more interesting, slightly more coherent behavior out of these models, but they're hard to do at scale. But you might imagine that, like, for my candidate model of scientific explanation, it's been trained to do relatively more interesting inferences, kind of like the kind that humans get as trainee scientists, where we're sort of expected to draw interesting inferences from data that help us to figure out sort of like what are the kinds of inferences we care about drawing. But yeah, so I think that's an interesting answer. I guess I'm like, so looping back to my original question, if it's okay, if I have enough time. Okay. Yeah, so looping back to my original question, I'm interested in so you were sort of arguing for Bayesian models, probabilistic programs as your claim was something like it's sort of the best way to think about the way that humans could do these kind of inferences. And I guess I'm trying to figure out, if you think, well, maybe, a GPT-like model that's trained on sort of slightly different tasks than next word prediction, if it's trained to read in sort of a description of an experiment and output a theory that explains that, how that data was generated and explains it in terms of knowledge from the world. If you think that that kind of model is a possible candidate for this, how are you coming to the conclusion that Bayesian models with probabilistic programs are sort of the right way to be thinking about this? Are you thinking that that model is just an implementation of those Bayesian probabilistic programs? It's sort of these details of how you do this amortized inference over this impossibly large space of programs? Or do you think that that's a fundamentally different explanation? And if so, what is the evidence you're using to dismiss that model given that, you know, as you said, GPT-3 can come up with plausible explanations some of the time, even though it's trained on a pretty silly task.
Right, right. So, yeah. So let me phrase it this way. Suppose that you came to me with the perfect Bayesian inference algorithm. So I could plug this Bayesian inference algorithm, probabilistic inference algorithm, I could plug it into my probabilistic programming system, and any query that I could ask, it could compute efficiently and easily, right? And so this may well be impossible, but suppose that you could do it. My first claim is that that would go a pretty long way to subsuming many, many different problems, right? It would do so in a way which has a lot of nice properties, right? I would have coherency. There would be no inconsistencies in the claims that it makes. Yeah, logical, probabilistic, consistency, coherency. The answers that I get would make sense, right? And so the question is, okay, what would you do in a GPT-3's case to extend that?